Hello everyone. Let's talk about the concentration. So I'm going to show you these 5 solutions over here. Let's take a moment to figure out which one out of these 5 do you think is the most concentrated. So hopefully we said 5. And the reason why most of us might have said that is because, as we can see, the color is progressively becoming deeper and deeper. So that means whatever solute it is that we are adding in the solution is responsible for the color. And we are adding, when we add more and more solute, the color becomes deeper and deeper. So we can predict that solution 5 has the most amount of solute out of these 5 solutions. So let's record that here. Solution 5 seems to be the most concentrated because it has the deepest color. And we made this observation only based on the color. So this one would be called a qualitative observation. And the aim for the lesson then is how can we quantify concentration. So when we are comparing two solutions in terms of their concentration, one of them is dilute and the other one is concentrated. So dilute is the one that has less solute, and concentrated is the one that has more solute. So in most cases, when you're comparing two solutions, they ideally have the same amount and same type of solvent, but the only difference then is the amount of solute that they have. So concentrated is a solution that has more solute, solution with more solute per given amount of solvent. And then your dilute solution will be the one that has, whenever I can write, dilute solution is the one that has less solute per given amount of solvent. So that will be less solute. So that means when you are asked to calculate concentration, if we need the exact amount of, exact ratio of solute versus solvent in any given solution, we are going to need how much of solute and solvent do we have so that we can compare the amounts among different solutions. So we need the amount of solute and solvent. So what this means is that concentration in general, the general equation for concentration will just be the part over whole, because we are trying to figure out how much solute we have in any given solution, right? So take a moment to predict what will the equation look like for molarity. So as we can kind of predict from the name has got mole. That means we will have moles somewhere in this equation. And it needs to be the amount of part over the amount of the whole thing. The equation for molarity is we have the moles of solute at the top. And for the amount of the whole thing, which means the solution, we put that in liters. So very specifically, it's not milliliters, it's not centimeters cubed, or just like any other unit for volume. It has to be liters, very specifically. And something else that is a very common mistake that sometimes people make is instead of putting the amount of solution at the bottom, they put the amount of solvent at the bottom. The reason why that's incorrect is because, as we said earlier, we need concentration is supposed to represent part over whole. So if you put the amount of solute at the top and the amount of solvent at the bottom, both of them, solute and solvent, are two different parts of a solution. So they're just going to represent the ratio of the two parts and not how much of one part do we have in the overall solution. So please don't make that mistake. Make sure you put the liters of solution at the bottom. In terms of the units, we normally just use an uppercase M as the unit for molarity, but sometimes you might also see moles over liters written as the unit, which makes sense because we are dividing the moles of solute by the liters of the solution. So let's take a moment to do this math. You have a sodium chloride solution and you are asked how many grams of sodium chloride are dissolved in a 0.5 liter sample of a 1.5 molar solution. So one moment. So if I go ahead and plug in these numbers in my molarity equation, remember molarity is equal to moles over liters, and I am given a 1.5 molar solution. We are not given the moles, so we are going to set that equal to X, but we are given the liters, which is 0.5. So when I solve for X, I end up with 1.5 times 0.5, that's about 0.75 moles. The problem is, the question is not asking for moles of sodium chloride. Instead, it's asking for the grams. So as we have talked about this multiple times in class, when we are doing conversion between grams and moles, we need the molar mass. So for sodium chloride, the mass of sodium is about 23, and the molar mass for chlorine is about 35.5, so that adds up to approximately 58.5. So that means if you have 0.75 moles of sodium chloride, and we know that 1 mole of sodium chloride is equal to 58.5 grams, we can multiply the 58.5 with 0.75, and that gives us 43.5 grams of sodium chloride, and that's your answer. So let's do that with one more problem. So let's say we tested water at our school building, and we found that our sample had 8 times 10 to the power of negative 5 grams of lead. If I tell you that the sample that we took was about 100 milliliters, let's go ahead and calculate the molarity for this. So once again, we need to do some conversions for this one because we are not given, for molarity equation, we need moles and liters, but in this case, we are not given either of them. So let's first go ahead and convert the grams of lead to moles. And to do that, we are going to need the molar mass of lead, which is about 207. So 8 times 10 to the power of negative 5 grams of lead. If I divide this by the molar mass of lead, which is 207.2 grams per mole, we end up with about, it's a very small number, it's about 3.86 times 10 to the power of negative 7 moles. So now if I plug this in my molarity equation, 3.86 times 10 to the power of negative 6, and then I divide that by liters. 100 milliliter is equal to 0.1 liters. That gives me 3.86 times 10 to the power of negative 7 molar solution of water that has lead. Now, the problem with this number is that this is way too small. If you are writing a report to indicate how much lead you have in the water, sample that was found at our school, then and you have to write this number like multiple times, you are probably not going to be very happy with that. So which is why in science we always try to find shortcuts for things. So this is why we have this other unit, parts per million. Once again, it's going to be the same thing, part over whole. However, this is parts per million. So similar to when we say percent of anything. So to calculate the percent, we just times that thing with 100. So this will be the same concept, but in this case, we times with 1,000,000 instead of 100. So we do ppm is equal to the grams of solute, which is your part, over the grams of solution, which is the whole, and we multiply this with 1,000,000. Now, for these equations, for molarity and parts per million, you are given the equation for parts per million on page 4 in your reference table, and you will have access to this on the regions as well. However, unfortunately, we do not have the equation for molarity given anywhere anymore. So you will have to memorize the equation for molarity. So let's go ahead and calculate the concentration of lead in that water sample in parts per million. So I gave you a 100 milliliter sample. The density of water, as we all know, is 1 grams per milliliter. So that means 100 milliliter is equal to 100 grams. And then we already have the grams of lead in the question. So to calculate parts per million, if I put 8 times 10 to the power of -5 grams of lead over 100 grams of that solution times 1,000,000, we end up with 0.8 ppm. And now this is time to decide if this amount of lead is safe to drink. So EPA, which is the Environmental Protection Agency, gave us the acceptable amount of the heavy metals and some other substances that are very dangerous for us. So they did a lot of testing to figure out what is the acceptable level of these things that we can have around us. So for lead, the acceptable level is 0.05 ppm. And what we just found is way more than the safe limit. So unfortunately, this water is not safe to drink because according to EPA, the safe limit was 0.05 ppm. But to make you all feel better, and just so you don't stop drinking water in the school building, these numbers were made up and this is not true. Our water is safe. So to wrap this up, imagine a scenario. You have 1 molar copper sulfate solution and it is in a 2-liter container. And then you take that solution and you put it in 2 different containers, and now both of them have 1 liter. Will that change the molarity? Take a moment to think and respond. The answer is it will not, because when we are saying that molarity is changed, that means we are changing the amount of dissolved solute, which is not what we are doing here. We still have the same amount of dissolved solute, we still have the same amount of solvent. The only thing that we are doing is changing the containers. So we still have a 1 molar copper sulfate solution in those 2 containers. So still have same amount of dissolved solute. Okay, so with that, we just have some practice problems. Let's take a moment to work on question number 1. So we are calculating the concentration of a 100 milliliter solution that is made from 10 grams of Kool-Aid. So the question did not specify if you need the answer in molarity or ppm. So in this case, you can just look at the given units and decide which one to use. So for the solution, we are given milliliters. Although we can probably say that this is a solution with water, and the density of water is 1, so 100 milliliter will be equal to 100 grams. However, we also don't know if the solution is only with water because the question did not specify that. So the best thing to do here will be to calculate our answer in molarity. So that means we are going to need the moles over liters. So let's convert the 10 grams of Kool-Aid to moles. We need to figure out the molar mass. So go ahead and add the masses of 12 carbons, 22 hydrogens, and 11 oxygens. I believe you get something around like 342. So if I take 10 grams and I divide that by 342 grams per mole, you end up with about 0.029 moles. And then we can go ahead and plug this in the equation. So 0.029 moles over 100 milliliter, which is equal to 0.1 liters. And that should give you 0.29 molar solution of Kool-Aid. Let's take a moment to work on the second one. Right, so here we are given the grams of oxygen and the grams of water, and this is extremely important. You are given the grams of water, not the grams of the solution. So, and it didn't say that you have this sample or this is already a solution or this was already a mixture. It's saying that you took that amount of oxygen and you dissolved that in water, which was already 1,000 grams. So that means when you're plugging this in the ppm equation, make sure that after you put the mass of your solute at the top, you add the masses of solvent and solute to get the total mass of the solution. So that would be 1,000 grams plus 0.0070. Now in this case, it will not make a significant difference because the mass of the solute is extremely small. But in some cases it might. So please don't forget this. So your answer here will be about 7 ppm. So let's go ahead and do the last one. Now here we are given the ppm and we need to find the mass of the solute. So let's plug everything in the ppm equation. You have 15 ppm equals x, because we don't know the mass of solute, over 1,000 grams for the solution times, sorry, it's not 1,000, it's 100. 100 grams for the solution times 1,000,000. So to solve this, we can go ahead and divide both sides by 1,000,000 and then multiply both sides with 100. So this gets cancelled. And now you have 1,500 divided by 1,000,000, and that gives you 0.0015 grams for your solute. And there you go. That was lesson 10.2. I'll see you in the next one.